Good afternoon, everyone. My name is Yunlong from George Mason University. I'm pleased to be sharing my research overview in USENIX Security 2024. My topic today is what if it's not enough fixing non-pointer dereference with contextual check. Non-pointer dereference or NPD occurs when a program tries to access memory as a non-pointer, and dereferencing it always causes the program to crash. When NPDs are exploited by attackers' malicious behavior like DOS, resource leakage, arbitrary code execution, and system-wide crash would be conducted. Several efforts have been made to patch NPD vulnerabilities, and most of them follow the conventional generate and validate repair steps. They first traverse the search space using classic search algorithm and then validate the generated patches using test cases. As a SOTA solution for fixing NPD errors, we reduce the search space using a predefined fixing pattern, like adding an if check. In general, they will determine whether the checked variable is null, and if so, the execution flow will be interrupted. Otherwise, the normal execution will be executed. However, this solution failed to take the valuable contextual information into consideration, potentially resulting in incorrect patches. In the following example, we will show what the contextual information in the SOTA approach ignore and how we treat them to generate the accurate patches. The first example shows that the valuable intraprocedural information, like the allocated memory and the occupied lock, should be released during patch generation. However, the SOTA approaches focus on checking the exception value and return directly when the pointer is null to prevent NPD issue, which may lead to the results occupation endlessly. The second example shows that a modified function argument should be reset before program exit. Otherwise, it may lead to a program to a chaos logic. In this example, the traditional approaches will check whether SRC is null and return true if so. However, the function argument R in the buggy function will be passed to the function caller and caller. Failing to reset variable R could make the function schedule work normally in the caller when the memory allocation fails in the buggy function. Then is the third example. In the buggy function, the failure allocation of KZLock will return a non-pointer to new TS, and the dereferencing it causes an NPD issue. To fix this, the SOTA approach checks the non-value and return directly considering the void function type. However, under such a case, the caller function will execute normally even if the failure memory allocation is the buggy function, potentially propagating the vulnerability. Therefore, we first generate the initial patch as the SOTA approach did, and then assess its correctness through the code chain. Function type modification and code chain assessment are required to fix this NPD issue. Our key contribution in this paper is that we propose CONCH to generate accurate patches for NPD errors by considering the contextual information, including the intraprocedural state retrogression, function argument resetting, and code chain assessment. CONCH consists of mainly 4 steps: the NPD contextual graph construction, path-sensitive fixing position selection, initial patch generation, including the memory freezing and lock releasing, and the final patch determination, including the global variable and function argument resetting and code chain assessment. First, we create an NPD tailored graph. For the potential NPD program, we construct the intraprocedural CFG and the one-hop calling function. The reason that we use one-hop calling function is that it can cover most of all real-world vulnerability cases, and we can also conduct incremental analysis if it is not enough. Then we apply the separation logic to localize the NPD errors. These rules include the load error, that the invalid memory can be loaded, and load null, that the non-pointer cannot be loaded. and the start error and the start now rules. After the fault localization, we can obtain the none position and that the pointer becomes null, and the error position that the error is triggered. Next, we simplify the obtained CFG by excluding the statements that are not between the none and error position. Finally, we construct the interprocedural CFG by merging the reverse statements and their calling functions. We also conduct the path-sensitive fixing position selection. Here, our key insight is to effectively fix the vulnerability and avoid introducing duplicated repair operation. Therefore, there are 4 different cases, including one null, one error, multi-null, one error, one null multi-error, and multi-null multi-error. We select the corresponding repair position accordingly, as shown in the above figures. After obtaining the none and error positions and the repair positions, we need to construct the repair operation. In this paper, we only focus on the cases that can be fixed by adding if checks, which is the most popular scenario in real-world vulnerabilities. In such a fixing framework, the first task is to construct the if condition. By analyzing all the NPD CVE record, we find that the if condition construction can be divided into non-check, exception value check, and non-check. The key to analyze the return value of the calling function at the non-position. And for example, the failure memory allocation of KV-malloc array will return a non-pointer to CPU sum, and the dereferencing is cause NPD error. To fix this, we can check whether the CPU sum is null and return directly without any value considering its void function type. Then we retrogress the local resources, including the memory releasing and the lock releasing. Here, the challenge is how to pair the required functions. We analyze the CV record and the open source repository to generate function pairs dataset by collecting the function parameter and their naming convention. And we obtained over thousands of function pairs, including the lock, unlock, malloc free, KZalloc free, etc. Finally, it's the return statement construction. In this step, we mainly rely on the function type as shown in the above figures. The first case returns false, considering the Boolean type. The second case returns directly, considering the void function type. In addition, some cases, the continue and break statements are required to exit the loop. After generating the initial patch, we conduct the interprocedural state propagation to generate the final patch, mainly consisting of 2 steps. The first one is to reset a global variable and function argument, which includes the global variable and function argument identification, and inferring the expected value from the data flow in the caller function. And second one is coaching assessment. The purpose for this step is mainly for the void function type. Please refer to the paper for more details. We evaluate CONCH on 80 real-world NPD vulnerabilities and 18 NPD errors in defect 4G benchmark. We conduct a comparison with SOTA approaches, including the VFix as a SOTA approach and NPE fix as an NPD repair and SIMFix as a general repair. All the experiments are conducted on machine with Intel i7 CPU and 16 GB memory running Ubuntu 22. When testing on CVE dataset, CONCH can generate 68 correct patches and 12 incorrect patches, outperforming the SOTA approaches with over 26%. As for the 12 incorrect patches, all of them are due to the semantic errors, which means that the patch generation requires the expert knowledge. For example, the first row shows one case that we cannot generate correct patches. The official patch checks whether the member reg prog of the RMP is not null. However, the member information and is not obtained in the context. Therefore, we can only generate the patch to check whether the pointer is not null. Similarly, For the CVE 2022-2874, the official patch check whether the variable is equal to a specific macro. However, the macro information and the relation with the macro cannot be obtained in context. Therefore, we cannot generate the accurate patch for this case. For the second dataset, CONCH generates 16 correct patches and 2 incorrect patches, outperforming the SOTA approaches. And the reason for the 2 incorrect patches is also due to the specific macro that are not in context. Finally, is a conclusion. We propose CONCH to fix NPD errors with contextual checks, and we are the first to address local results retrogression and reset global variable and function argument in NPD fixing. And our results show that CONCH can outperform the SOTA approaches. That's all for my presentation. Thank you for listening.